Okay, so we looked into the what is edge detection and how the convolutional neural network actually looks in tries to find edges in an image, and then we looked into the disadvantages or the damage that may create, that may cause when you apply a convolutional neural network, and then the remedies, right? Padding and stride. Right? Stride is not a remedy for these problems, but stride is to consider less number of pixels, um, uh, to speed up the process and reduce the number of calculations, kind of a thing. Okay, so we looked into a small neural network also yesterday. Right. So this concept I'll just reiterate and then we'll go into the code. Okay, so here there are three channels in the image, RGB. In a satellite image, right, there will be 12 channels. Satellite image will have infrared and all the, there are other channels also. In a normal camera, you will have three channels. The picture taken using normal camera will have three channels, but the satellite imaging kind of stuff, right, will have more channels here. So I have three channels here, and when I'm trying to say the filter size is 3, I'll just specify 3 only or 5. Right? 5 by 5 by 3 will automatically be chosen because of the previous layer's number of channels. And any number of channels you have, when you apply convolution filter, you get a two-dimensional matrix only. That's one point you need to remember. Any number of channels, one filter will give you one two-dimensional matrix. Right? You want to identify vertical edge, you need to use one filter that will give a vertical edge detected two-dimensional plot, the two-dimensional matrix, and horizontal edge another filter. You apply, you get another, right, like this. Right? Horizontal, vertical, you get two, matrices. Then you are applying bias term. It's a broadcasting, and then you apply ReLU, and this is the outcome. After nonlinear function is the outcome of a next layer. So this is one layer, and this is the outcome of that layer. So like that, you can actually take multiple layers and then you add a fully connected layer at the end. We call this dense layer as fully connected layer. Okay, so you understood this network structure, right? So F is the filter size, filter dimensionality. If I say 3, it is 3 by 3 by number of channels in the previous layer. I say 5, 5 by 5 by number of channels in the previous layer. 5 by 5 by number of channels in the previous layer. 5 by 5 by 20, right? So the dimensionality is reducing, right? At one point in time, we'll talk about a thing where we will try to create some n by n by 1 dimensional matrix. That's like almost flattened network. I'll talk about that today. So leave that. So any questions here on this network, or the parameters are?
Yeah. So actually, are we applying these filters in all in the input layer also?
Filters, yeah. This is input, right? And
Yeah.
on input layer, we are applying filters.
Where is this processing, this applying for filter, the 10 filters is happening? Is it on input layer?
Yeah, input layer. If you look at this diagram, suppose that this is input layer. Instead of 2, you have 10 there, and you get 10 two-dimensional matrices, and then the algorithm will apply the TensorFlow code will apply bias term and then apply ReLU. You get this 10-dimensional, right? 37 by 37 by 10 you are getting here. Is that a question or?
Yeah, yeah. That's the question. But in the deep neural networks,
Uh,
so the input layer is just acting as a input supplier, like X1 to Xn.
yeah, any layer,
Whatever is happening, it is.
any network input layer is the input. Whatever whether you pass one record or 32 records or 64 records or 16 records, Right? The input layer is just the input, that's it. No, it's a batch.
Okay, but this applying filter 3 of f equal to 3 and 10 filters is actually happening. The processing is actually happening on the convolution layer 1.
This is convolution layer 1 and this is outcome.
Okay.
No, the filters are the layer. You are actually trying to understand in the way the deep neural network we demonstrated, right? In
Yeah.
deep neural network, we will actually show the nodes, but here we are showing output.
Okay. In the node, actually, all the processing is happening.
Filters. Right. The filters dimensionality is the node actually. These parameters are the nodes, 10 nodes. But in convolutional neural network, it is called as filters. No? You're actually thinking. You're actually trying to correlate. Did you guys get what Shishram is asking about? That's the minor difference in the way we represent the networks, deep neural network and convolutional neural network. Did you guys get it? Did you understand his question?
Yes, sir.
Clear, right? Yeah, this is the network actually. No, we are not showing nodes here. We are showing the outcome. But in deep neural network, right, we will not show outcome. We pictorially, at least pictorially, we will not actually show the outcome. We will show the nodes there, ReLU nodes and all that. Okay.
So the function is only a ReLU or any other function?
We can use any function. I'll show you code again. We can use any activation function.
Sir, before that, just one question, sir.
Please.
On the same diagram, can you please go to that diagram?
Yeah.
Small question. Yeah, here, if we observe this carefully, the number of filters layer by layer slowly it increased. Is it the right? Is it the right approach to from one layer to another layer to increase the number of filters? Is it what is
Yes,
the right
sir.
approach, sir?
Yes, that's the convention basically. 10, 20, 40. You double the number of filters.
Okay. Okay.
Double the number of filters. Doubling number of filters is like you're trying to understand 10 features here. On those 10 features, you are trying to understand 20 more features. On those 20 features, we are trying to understand 40 more features. When I say 40 filters, 40 patterns it's going to identify, right? 20 patterns, 10 patterns, or edges.
Okay.
Yeah, that's a convention. Basically, it worked. I think it's a heuristic.
Okay.
See this here also. I said 3, 5, 7, 9. Right. Filters 3, filters 6. Okay, sorry. Yeah, kernel size is the filter. Okay, filter size 3 by 3, 5 by 5, 7 by 7, 9 by 9. Filters are the number of filters. Okay, I think yesterday I said in a different way. I think filters are the number of filters. Right? Do you want to 3 filters with 3 by 3 by 1? Because the previous layer, the input layer dimensionality is 1. Okay, so 3 by 3 by 1. Even 3 by 3 matrix or 3 by 3 by 1 is same, but it needs a 3-dimensional matrix. The input also 3-dimensional and the filters also in 3D. Now anyway, we used 3 filters, right? The outcome is going to be right 28 minus f, right? F is 3, right? 28 minus f plus 1. 28 minus 3 is 25. 26 by 3 is the output of this now this layer 26 by 26 by 3 is the output, and then we are applying 6 filters of size now 5 by 5 by 3. 5 by 5 by 3 is the filter. When you apply this filter, 26 minus 6 plus 1 is 21. 21 by 21 by 5 is 21 by 21 by 6 is going to be the output. Number of filters are 6, right? 21 by 21 by 6, right? And now here you will get 21 by 21 by 6, and then the filter size I said kernel size 7. 7 by 7 by 6 is the filter size. Filter dimensionality 7 by 7 by 6 is the filter dimensionality. We are applying 12, so 21 minus 12 plus 1 is 10. 10 by 10 by 7 is going to be the output here, right? 10 by 10 by 7, and again you are applying to 24 filters. 9 is the dimensionality. 10 minus 9 by plus 1 is 2. 2 by 2 by 24 you get as the output here. Now if you see summary, I don't know, I did not do summary somewhere. I think I can do summary. Let me do the summary. Model.summary. So previously in 1.14 and 1.15, right, we don't have this summary thing in TensorFlow. So we need to manually calculate and understand how the outcome is coming. Now it is easy. See,
Maybe after fit we have to.
Spelling mistake, I think.
Yeah, here it's a spelling mistake.
Yeah, I forgot, I think. I think my calculation was wrong. See this 22 by 22 by 6 and 16 by 16 by 12, 8 by 8 by 24. And now we flattened it. Flattening is nothing but 18 to 18 to 24. That many it will come. Okay, and then I added 120 to 216 layered dense, dense layer, 108 dense layer, and 10 dense layer, and I used Atom optimizer. Okay. Here I am using image data generator. Okay, I'll explain this in a moment. Okay, let me execute that. It's taken a bit more time than. How many epochs I've kept here? 10 epochs. So it's a CNN network on the same, digit recognizer data set. So it takes some time. In the meantime, right? Let us understand about image data generator. So when your data is already present in memory, right? Already this fit method has got batch size, but this image data generator provides us a way to create batches. Okay, so is this useful? Yes, we'll see. On a bigger data set, right? This is a lot more useful than here. So here, rotation range, zoom range, width shift range, and height shift range, and some things I gave, right? This image data generator actually works as a data augmenter. What is data augmentation? If you have a cat image, if you tilt it a little bit, right, it'll be a separate image, different image. Okay, let me try to draw and explain. Okay. So this data augmentation, right? So if you have a cat image, right? If you tilt it a little bit, it will be like that. When data is less, we have less data, you may have to create multiple images out of the existing image, right? So that's like if a cat is actually walking on a slant space, right? The model will understand that is also a cat. Basically, what model is trying to do, the pixels and their patterns it is trying to understand, right? So if you flag this as cat and this also as cat and pass these two records, instead of passing one record, you are passing two now. You can actually create 10, 12, maybe different images out of the same, right? Maybe like that. One more cat you can create, right? Maybe you can create a cat like this, but never a cat is picture is going to be like that, right? So you can create like that, multiple. You take one image and creating multiple images. That's called as data augmentation. This data generator will actually do that. These rotation range, zoom range, right? You can actually zoom the image also, right? Width shift range, right? These are all image related stuff. You look into the API, you'll understand. Basically what we are doing is, even if you have 10 images, you are trying to produce maybe 200 images by doing data augmentation. Okay, so this will actually create that data, and then from that data it will pull out batch size 60. Originally you may have passed 100 images, but you will have 2000 3000 images generated by this one, and you pass a lot of data and the model gets trained well. That's the data augmentation part. And we have these kinds of methods here. Even in TensorFlow we have a data set, one class, and I'll talk about that maybe um, when we look into NLP, right? I'll talk about that. Okay, so any questions here? Did you understood? So instead of passing X and Y, we are passing data augmenter here. So that will actually generate your needed X and Y and then pass it. Okay.
So it's actually increasing the number of input records, right?
Yes.
Okay, how many is it increased here in this particular case?
We don't know, right? It depends on these hyperparameters, these parameters. Yeah.
Okay.
If you look at the API, right? I don't remember basically. I don't
Yeah.
know, but I don't remember. Look into API and you'll understand. Yeah, knowing number of records is also important because it determines how much time it takes and all that, right? So we have got 97% accuracy. What I did save model? I think the method is not there. That's okay. So while predicting, see this here, I actually converted my image into a 4-dimensional matrix. Why? Can somebody tell me? Let me try to run this. Right. Let me show you the shape of it. See that I converted a 2-dimensional image into a 4-dimensional. Right, before I actually ask it to predict. Let me comment this out. This code, I kind of, the function is not there. So I converted the image and now I am predicting. Predict class is not going to be there. So, what? Okay, sorry. That history will have some statistics where you can actually plot. I'll show that later. See that it actually predicted a one-hot representation. right? The record belongs to 0, 1, 2, 3, 4. So why did I converted this picture into 4-dimensional? If you look at the network, right? Here I said the input shape is 28 by 28 by 1, but we are passing a 16 record batch, right? So it's going to be, in NumPy, in NumPy convention, it is going to be the input layer. The dimensionality is going to be 16 by 1 by 28 by 28. Right? That's the input. When you are passing, when you are in production, right? When you are actually when you are asking for prediction, you should be passing in this dimensionality only. This one is dynamic. You can change it. Okay, this one is dynamic, but this is fixed. So when I say the input dimensionality 28 by 28 by 1, the each record should have this dimensionality, but the additional dimensionality, this one, is dynamic, because you are passing a batch. While training you may pass 16, but in production you may pass 100, R1, right? R10, it doesn't matter. So you may pass like this, right? So you pass 100 records, you'll get 100 outputs. Got it? Got it? Why did I convert my picture into a 4-dimensional picture? Got it, right?
Yes.
Okay, so there is one more concept we need to understand related to the layer, which is max pooling or average pooling. So when we are doing padding and stride, we are actually um, adding more zeros around the picture, or we are actually sliding. So the way we slide is actually changed, right? In max pooling, if I say 2 as the max pooling size, right, it's going to take maximum number from that matrix. This is the whole matrix, whole data, and it takes 2 by 2 matrix and takes maximum and gives as output. Right? This is called a layer, max pooling layer it is. Okay, but there is no activation function as such. It is just an aggregation function, not an activation function. So whether you want to take max or average. No, average pooling means you take all these numbers, sum it, divide by 4, you take the average here. Okay. So here also max pooling, here also max pooling. Why do you use max pooling? To reduce dimensionality quickly. You have a big picture and with a lot of big pixels, you think most of it is not useful, or the in a 3 by 3 area or 5 by 5 area, or or 4 by 4 area, out of 16 pixels, if you take the maximum numbered pixel, it is enough. It is like um, reducing the quality of the picture, right? Quality of the picture. You have a HD picture, you want to reduce the quality to maybe normal picture, so that uh, you can save it well, or the size of the picture you are trying to reduce, like that it is. If you take the maximum pixel there, it will actually suffice, because in a picture, if you observe, right, I think that one, let me give you 1 second, I'll show you one thing here. Now, why max pooling works? I'm actually trying to explain. I think you must have remembered in binary class classification I showed you. See this here, see this here? It is a handwritten 5, right? If you look at this area or any area which is, where the stroke is high, see the numbers are all kind of in same, right? If you take 2 by 2 matrices, right? Those numbers are all kind of close to each other. Observe? Do you observe? If you take one number from these, right, it is going to kind of create the same, same kind of, it's going to generate same kind of picture. Right? If you apply max pooling on this and try to see, right, so maybe 2 by 2 matrix, right, so it's going to, it may actually make the image a little thinner than than whatever we are seeing here. Okay, so that kind of effect it is going to have. Max pooling will have that kind of an effect. So sometimes we may have to reduce the dimensionality quickly. In that, we will add max pooling as an additional layer to the convolutional layer. See this here? There is a convolutional layer, right? The outcome, we applied max pooling, we reduced the dimensionality, right? 2 by 2, right? We reduce the dimensionality. Again, convolutional layer, we got the output, applied max pooling, we reduce the dimension. So quickly the 32 by 32 by 3 image actually became 5 by 5 by 16, right? 400 pixels. Sometimes this also may work, right? This actually reduces number of calculations, right? Model network actually executes faster. The model may work without max pooling, but when you apply max pooling, also it may work. It reduces the um, number of matrix manipulations on the processor. Got it? You can take max or average. Yeah.
Sir, there may be some hit on the accuracy of the prediction. No?
Yes, and it may be, it may not be. We have to see, right?
Okay.
It's an experimental thing, right? So
Okay, sir.
it is like applying max pooling is also giving you the same accuracy. You'll use max pooled because it's going to be less in resource usage, right? The processing and all.
Sure. Okay, sir.
Okay, so the other point is that we consider this whole thing as one layer, the convolutional and the max. I think I should have kept this till here, right? This arrow. Convolutional and max pooling both are called as one layer only, because the max pooling has got no activation function. It is just an aggregation. We kind of, the outcome of convolution we are aggregating. That's it. Okay, outcome of convolution. Generally, the max pooling is used in combination with the convolution layer. The question is like this, can I use the max pooling on the original image? Yes, but it is not the way, it is not the convention to use it. The convention is that max pooling is used along with the convolution layer, and those two combined is called as one layer. This is one layer again. And the outcome we passed it to dense layers. Okay. So that is the convolutional neural network theoretically. Let me see any other code files are there on this. Yeah, so transfer learning is the next concept. So I need to cover a little bit of theory there. Digit training around big image. What big image? What is this? The same thing, right? Same code it is. Why did I save it as separately? I would have done some experiment here. I don't know what I did. Good. Okay, got it. So here, right, I'll explain this. Yeah, fully connected, fully convolutional layer also I built. So yeah, this is a good example. This is a good one. This is the basis for object detection. Okay. So yeah. Okay. So next thing is Right? Transfer learning, we need to understand. What is transfer learning? Right? Before we go there, right, we already understood all these concepts, but I'll just reiterate. Right? Advantages of using convolutional neural network. Imagine, right, a matrix, input matrix is 5000 by 5000 by 3. Right? It's going to be 75 million pixels. Right? If you have a 100 layer neural network, 75 million by 100. Right? Each neuron, if it's a deep neural network, each neuron needs 75 million weights or parameters. Right? And 100 into 100, 75 million into 100. It's going to be huge. And the memory usage is going to be very high, and processing cannot happen. Matrix manipulations cannot happen. So in that case, right, if you take on the same image, right, if you take a 3 by 3 filter with 3 channels and a bias term, it's going to be 28 weights for each filter. It's going to be 28 weights. Even if you take 10 of them, right, it's going to be 280. Right? And then you are doing convolutional neural network, and you are identifying the patterns there also. Right? You may not be identifying all at once, but this is advantageous because in a picture you will have different patterns. So this 3 by 3 by 3 may identify one pattern, and that same pattern is used. The same pattern recognition is used throughout the image. Right? There is a vertical line in an image. If you have vertical, edge detector, it will identify all the vertical lines in the image. Okay, so this reduces lots of weight on the model. Along with that, parameter sharing is going to be there. Right? One filter which identifies vertical edge will identify vertical edge throughout the image. One filter which is identifying horizontal edge will identify horizontal edge throughout the picture. So like that, that's called as parameter sharing. Okay, CNN came in as a solution to to the problem of DNN. DNN occupying too much memory can be reduced can be solved by using convolutional neural network. Got it? So sparsity of connectivity and parameter sharing are interview questions. Sparsity of connectivity means in each layer, each output value depends on small number of inputs. Right? So if you take this cell depends on only these 27 values, or 28 values, or maybe 27 values only. Right? So here also it depends on these cells, right? They depend on. So it is called a sparsity of connectivity. Okay. So in deep neural network, each output, right? Each node's output depends on. If you have 75 million input value, 75 million weights it depends on. So it need to adjust 75 million weights. The algorithm need to adjust 75 million weights. But here it can adjust these 27, and it's going to be quicker. The pattern recognition is going to be quicker, especially on images. CNN is useful on the data where dimensionality is huge. Okay, and the second thing is how the W will get, these are all weights, right? These are all weights. These 27 are weights. These 27 are weights. How do they get adjusted? Again, gradient descent algorithm only. W1 is equal to W1 minus alpha into derivative of the cost function with respect to W1. W2 is equal to W2 minus alpha into derivative of cost function with respect to W2. W3 is equal to W3. That is back propagation on the convolutional neural network. Got it? How back propagation happens on a convolutional neural network? Did you get it? I think you already would have understood. Okay, so let us try to understand what is transfer learning.
Sir, before we go, can you please go to the pooling, sir?
Pooling, okay.
So what is F equal to 2 here, sir?
Pooling size. Original image is a 4x4 image, right? Pooling layer filter size is 2. Pooling layer, the filter size of pooling layer is 2. That means it considers 2x2 matrices. And I said stride is equal to 2, so it jumped 2. If stride is 1, right? That's a good question. I think I'm actually jumping the guns here. Give me 1 second. That's a good question. Okay, so here, if my stride was 1, this is 2, right? If my stride was 1, what would have happened is, it would have taken the max of that area, right? That is 9. Max of, stride is 1 means, if you don't specify stride, max of that area is again 9, right? Max of that area is what? 8. Max of that area, right? It's a convolution I am doing. Okay, 9. Max of that area 9. Max of that area 7. Max of that area 9. Max of that area 9. Max of that area 7. This would have been the output. If stride is equal to 1 with filter size 2, it is always considering a 2x2 array. If it is it's a 3-dimensional picture, right? It's a 3-dimensional picture, right? It would have considered a 2x2x3 on that area, right? Like that. In all those pictures, right? 2x2x3 means 12 pictures, which is the maximum it will take. When you apply max pooling, also the outcome is going to be a 2x2 matrix only. Generally, you will not have 3x3 matrix max pooling, because you already applied convolution. The outcome is going to be 2-dimensional. On 2-dimensional, you are applying max pooling. Got it? Generally, you will have 2-dimensional matrix only. Generally you will apply, the network will apply max pooling layer on a 2-dimensional matrix only, because this is a max pooling layer is after convolution layer. Got it?
Yes. I think this stride we can specify as a tuple, right? A tuple of integers, 2 numbers.
Yeah, in previous, there was a convention to specify like 2 comma 2 comma 3 comma something. That's in API, right? Previously it used to be there. I don't know whether it's there or now. Let me go to that. So int or list of ints, yeah, that actually, this is for the rows, this is for columns, and this is for depth, right? If you specify tuple, right? So the stride of a sliding window for each dimension of the input. If the single value is given, it replicates a h width dimension, height and width only. By default, n and c dimensions are set to 1. The dimensions order data format. I think list of ints that has the length 1, 2, or 4. Right? 1 means for all the same stride. 2 means rows and columns. Two values if you pass. Row how much stride you should do, column how much stride you should do. Right? stride when you are doing, right, there are two directions, right? This direction and this direction. And how much you should stride on this direction, how much you should stride on this direction. But they said 4 there, right? If you give 4 values there, a list of 4 values for stride, yeah, filter height, filter width, in channel, out channel, right? So this is the rows and columns, right? Filter width, filter height. This is rows and columns, and this is the input channels, right? How many channels, and output channels. So filter, number of filters, right? See, stride 1 1 1 1 in the past, right? So if it is 1 and 1, these two are actually related to batch and the third dimension. I think this is for third dimension and this is for batch. I think, you know, but in batch also, do you want to do a stride for, you know, if you say 2, right, here, first record it may do stride, second record it may not do stride, then dimensionality will change, right? If it is not doing stride, dimensionality will change. I think this one 4 values. This is the problem with the TensorFlow. Documentation is not that clear. Give me 1 second. Filter height, filter width. We are generally giving it a 2-dimensional square matrix there, right? And this is batch size only. Out channels, in channels. Out channels. So if you give 4 values in stride, what happens? That's the question I am actually trying to answer. The single value is given, it will be taken for height and width. What about the depth? What about the depth? Did you understood my concern here? So I am thinking, like, you know, this one is for row, this one is for column, okay, this one is for depth, okay, till that point it is good. But this one, right, I am thinking it is for batch, you know, batch, right? The first record you apply stride, second record you don't, third you apply stride, fourth you don't. That's why I'm thinking if you say 2 there, right? If I do that, right, it's going to be a problematic thing. If you apply stride, the dimensionality of the output is going to be different, right? The square matrix it's going to give is going to be smaller. If you don't apply stride, the 2-dimensional matrix is going to be big, right? So this fourth one is not belonging to the batch, I think, something else. Did you get it?
Sir, at least from my side, I'm not thinking like that. They are only individual strides only, each of them. Just that each one corresponds to some combination. Somehow, I'm just guessing like that, sir.
Kaadandi. It is actually, you know, when you pass only one value, like in the networks I am doing here, and I would have passed stride is equal to 1, I passed, right? If I say 2, right, it's going to take that 2 to all dimensions, right? Row and column basically. Right?
Okay.
Depth anyway is considered there, right? So for whole, you know, matrix it will consider. But if I say 1 1 1 2, right, for rows it will jump only 1 column, and for columns, right, it will jump 2 rows. in this direction it will jump only 1, in this direction it will jump 2, 2, 2, like that.
Okay. Okay.
Yeah, but the other two, right? Other two, if you R4, they said, right? When 4 is given like this, what happens? That we need to see. Maybe we can experiment, right? We can actually pass data and see the summary. You will find it, right? I'll do that. Maybe that's here. I'll do. Okay, so let me. Oh my goodness. Two integers. Where is it? Yeah, 2 integers. It's okay, but then here in the documentation is it 4, right? An int or list of ints that has a length 1, 2, or 4, right? Guys, did you see this?
Yes, sir.
When I
Somewhere,
give 4,
somewhere also I read only 2. So it's
this is one.
a
This is
tuple,
1.2.
a single value or a tuple with 2 values.
But here his official document is, maybe it's a mistake, maybe by those guys. So if I say 2 here, right? It's going to do. Oh my god. The dimensionality must be same, maybe. So the calculation, actually came wrong. Actually, this it is not giving you a two-dimensional matrix. Maybe that's where. So maybe let me put 2 here and 4 here. This is where you need to understand the formula, right? N minus n plus 2p minus f plus 1, n plus 2p minus f by s plus 1. You need to understand the formula. If you don't understand the formula and try to do this, right, it's going to create these kinds of problems. If I say 2 2, it will work. For this particular image, the dimensionality is not matching. So 3 3 12 and 9 9 12 24. That is. Let me give 2 slide here. Something wrong. Some calculate some. This they said straight 2. What happens? Filter size 3, right? 28 minus 3 plus 1. 28 minus 3. 28 minus 3 is 25. Okay, that's the problem. 3 if you give it works, huh? 28 minus 3 is 25. Sorry. 2 is 26 divided by. Sorry. 28 minus 3. 28 minus 3 is 25, right? So, yeah, if you give 4 here, right? 28 minus 4 is 24. Divided by 2 is 12.
The changes happened only once on the one filter.
This is actually dilation. Dilation and other concept is there. They are actually related to picture. Tried 1 1 1 1 only they took. On this particular image, it may not be matching, but you can give straight 2. Maybe let me do this one here, 2 here. I think let me restart the kernel. So now the formula is 28 plus 2p 0 minus f is 3 is 25 divided by 2 will not work. Divided by 2 will actually take the floor, that means 12 it will take, plus 1 13, right? So it should be 13. If I say 2 here, it should work. Let's see. Negative dimension size caused. Okay, got it. I think we have too many layers here. By end of this, right, it is actually causing a negative layer. That's the problem, right? We have too many layers. No, previously we had if stride is 1, right, we had how many? What is the output here? 22, right? Guys, are you understanding?
Yes, sir. If we increase the stride, the dimensionality reduces.
Dimensionality will fall, right? And then by the time it reached here, it actually was kind of 8 by 8 by 24. And now we are trying to apply, kernel size 9, right? 8 minus 9, it is causing negative number, right? So that's the problem. Okay, now let us try to put 1 comma 1 comma 1 comma 1 and see what. Why 2? It will expect 2 only. You should not put 4. I don't know. And they said 4 there, and in the code, in the output also it is showing at 1 comma 1, right? So if I say 1 comma 2, right, it works. See that? 1 comma 2 is also working. In the rows it is applying, in the columns it is applying something else, I think. So 22 by 22 by 6 only it got. In the first layer. Yeah. So on the rows, if different stride is given, we don't have formula to calculate, right? Manually I cannot. Is it taking? Oh, I did not ram that below statement. Summary I didn't ram. See that? Right? Rows, it is actually doing 1 stride. Columns it is doing 2 stride. So the number of columns reduced, right? Got it? So I think it should take 4 values, but it is not taking 4 values. Maybe let me put it as a tuple. In the API they said 4, but it is not taking 4 values. I don't know why. I don't know. I don't know why. That's okay. That's okay. But you understood the concept, right?
So maybe for 4 values, the input maybe of the corresponding dimension.
No, sir, because we are passing 3-dimensional array, right? So convolutional, Conv 2D expects 3-dimensional array. That's another point. Conv 2D, it is actually doing 2-dimensional convolution here. If you see this, right, this is 2-dimensional convolution. That 2-dimension, that 2-dimension, that 2-dimension, that 2-dimension, that. This is convolutional 2D. Okay. We have Conv 1D. We'll see Conv 1D, which expects a 2-dimensional array as input. Okay, in word embeddings and text processing, right? We'll see Conv 1D, which will actually do 1-dimensional convolution. It will just do that way and that way and that way, like that. It will actually go row by row, right? And Conv 3D means it actually does this direction, and that direction also. In the depth direction also it will do. Okay, it will stride depth direction also, and it will give you a three-dimensional matrix. When you do Con 2D, you get two-dimensional matrix as output. This one. Do 3D, you get three-dimensional matrix as output. If you do Con 1D, you get one-dimensional matrix as output. Vector as output. Okay. Got it?
Yes.
We are doing Con 2D, so I passed shape is correct and I hope this is good. So this is good, you know. I think I am doing experimentation, but you should be doing it. So but your questions are very valid, and you try to do the experimentation. So let us maybe try to cover this transfer learning tomorrow. Right? It's a simple concept. We already know. Right? In gradient descent, how the theta is being learnt is the way transfer learning works. At that point, I actually showed you in the beginning of the that deep learning itself, right? So every iteration or every epoch, the theta is moving from where it is, right? Suppose that you saved the model at one point in time and loaded the model again and then started training there. Instead of initializing the values randomly, you are taking already pre-trained weights. Suppose the job is same, you identified animals previously. You built a model to identify 10 animals previously. Now you are trying to identify 10 more. You can use already trained weights because they already know a little bit of knowledge about animals. Instead of initializing randomly, if you take those weights, the learning is going to be faster with less data, right? Deep learning algorithms are data hungry. They need lots of data. To avoid that problem, we have to use pre-trained models, and pre-trained models load the weights and then train again from the weights we loaded, from where we actually loaded. So that actually solves the data hungry problem. Even if you have less number of images, you can train. We'll see that in object detection. I'll show you how to do object detection model. In there we'll see already pre-trained models we'll use, and we actually with 100 images we'll actually build a beautiful neural network. Okay, so that is transfer learning, and how to do that code and all I'll show with an example tomorrow. Concept, you got it, right?
Yeah, yes.
So there are transformer networks and transfer learning. They're a bit sound similar, but they are different. This is transfer learning. Transformer networks I'll explain later. They're more advanced and most recent findings in deep learning, and they are used for word embeddings in on text. Okay. So that's it for today. So let me stop recording.